Hello everyone, we are Group 1 and we are going to report the chapters 3 to 5 of Logic Design and Switching Theory. I am Christian Lordenz A. APARICI and my fellow members are John Bernard BARNUEVO, Francis Mark CAYCO, Dainty FARISCAL, Micko Luis Garcia, Justine Mark LIRAG, N PACLIAN, Reynel SOLIVEN, John Michael Vincent TORRES, and Helen VILLAR. So to start with, I'm going to report about K-maps. Kernel maps. So what is kernel map? It is also known as bridge diagram or K-map. This was invented in 1953 by Maurice Kernel and it's a graphical way of minimizing Boolean expression and it's reduced the cost and quantities of logical gates. K-map consists of tables of rows and columns with entries represents ones or zeros. And an n variable K-map has 2 raised to the power of n cells with n variable truth table value, and each cells refers to a min term or max term. So for the simplification process of K-map, groupings should have no diagonals. Next, only 2 to the raise of n cells in each group, and groups should be as large as possible. Next, a group can be combined if all cells of the group have the same set of variable, and in groupings, overlapping is allowed and fewest number of groups is also possible. So to give an example, I'm going to play a video that I recorded earlier and have fun. So hello everyone. To give an example for a K-map, we have here a truth table and we are going to consider these values and convert it into K-map as well as to give the function or to provide the function or the Boolean expression of this truth table. So as you can see here, we have here the 3 variables. We have 3 variables here, and to identify how many min terms we have 2 raised to the n, which is the 3 variables equals to 8 cells. So 1, 2, 3, 4, 5, 6, 7, 8. And let's try to plot our K-map. Since we have A, B, C, we have to put here A, B, and we have to put here letter C. So for A, B, since we have 2 binary here, we have to follow the gray code, the 0, 0, 0, 1, 1, 1, 1, 0. So the first binary represents letter A and the second binary represents letter B. So sa C naman, since isa lang siya, we have here the 0 and 1. So let's start. So for the first row, we have 0, 0, 0. Anyway, by the way, yung mga ilalagay natin sa min terms na to ay yung mga functional value ng truth table dito. So bali ito sila. So for the first row, we have 0, 0, 0 and we need to locate where is the 0, 0, 0 here, which is ito siya. And yung functional value niya is 0, so ang ilalagay natin dito is 0. The second row, we have the 0, 0, 1, meaning 0, 0 yung letter C niya is 1, so ilalagay natin dito is yung functional value niya, which is the 0. So for the third row, ito, take note of that, 1 na yung functional value niya. So 0, 1, 0. Hanapin natin yung 0, 1 sa AB and yung letter C, yung 0. So dito siya nakalagay. Ilalagay natin dito is 1. So for the next column or row, the 0, 1, 1, 0, 1, letter C, 1, and yung functional value niya is 0. So ilalagay natin dito is 0. So next row, we have 1, 0, 0. Hanapin natin yung 1, 0, 0, 1, 0, 0. So dito siya nakalagay. And yung functional value niya is 1. So 1. Next column is 1, 0, 1, 1, 0, and letter C1. So dito siya. Functional value niya is 1. So lalagay natin dito is 1. So next 1, 1, 1, 1. So yung last 2 row natin is 1, 1. So dito na siya. And yung letter C, 0 dito. Lalagay natin yung functional value niya which is 1. While the last is the functional value is 0. 1, 1, 1. So yung functional value niya is 0. So lalagyan 0. So for the next step, we have to group this in order to define the function or the Boolean expression of this truth table or this K-map na. So dito na tayo nakafocus sa K-map. So we can group these values into 1. Pwedeng sa 1 or pwedeng by 2s, by 4 or 6. Basta divisible by 2. So we have 1, 1 here na magkatabi. Basta bawal lang siyang diagonal. 1, 1 na magkatabi dito and 1, 1 na magkatabi dito. So to give the function of this, as you can see here, we have the 2 binaries, the AB, AB. So, as you can see here, we have 0, 1 for letter A. So, meaning, 0, 1 siya, hindi siya pares, meaning hindi dependent yung value na to sa A. But as you can see here, yung B is parehas na 1, meaning dependent yung value na to sa letter B. So we will put letter B here, and as you can see, these values also corresponds to letter C or the variable C, which is 0. So since 0 siya but nagko-correspond siya sa value na to, ang lalagay natin dito is letter C, but since 0 nga siya, magiging not C siya. And let's put a plus this or sign at ito namang group na to. So as you can see here, yung C niya is 0, 1 at magkaiba yung value ng letter C, meaning hindi na agad siya dependent sa value na to. But the letter A and B here is pareha silang 1 and yung 0 is pareha silang 1. So nagtutugma yung mga value nila. At ang gagawin na natin is ipuput natin yung letter A at yung letter B nito. So as you can see here, yung letter A is 1. So tama lang siya. But yung letter B natin is 0. So magiging not B siya. And ito na yung function natin. At para ma-check yan, pwede tayong mag-substitute from this truth table. So as you can see, let's try this third row. Itong 0, 1, 0 for ABC. So for letter B, 1 siya. So magiging 1. And yung C niya is 0 but it is not C. So magiging 1 din siya. Plus A, yung A natin is 0. And yung B natin is 1 but not B siya. So magiging 0. So ang value nito is 1 plus 0 equals to 1. So para ma-check natin, tama ba ang functional value niya, which is 1 and 1. So na-confirm natin na tama yung function na to kasi yung functional value niya is same dito sa na-check natin. So to check that, tignan natin. So ayan, tama nga yung nagawa natin. We have function is equals to B, C prime plus A, B prime. So the next stage or the next process is to transfer this K-map into circuit diagram. Pero ito na yung function natin. Ito na yung gagamitin natin. So ito na yung K-map natin. Basically, tapos na siya. But to show the circuit diagram of this function, ayan. So F is equals to B, C prime plus A, B prime. B prime siya. So we have two AND gates here. Siyempre, yung multiplication is represented as AND gate and the plus sign is represented as OR gate. So first we have the first gate is the B and C prime, and the second gate which is the A and B prime, and yung AND gates, and nagko-correspond siya sa output na itong function na to, which is the OR gate or the plus sign. So as you can see here, if you double check it sa mga circuit diagram, ito parehas lang yung mga true value nila or the functional value. And that's all. I hope you understand, and thank you.
Good afternoon. I'm John Bernard A. BARNUEVO, and I'm assigned to talk about the power of NAND and NOR gates in digital electronics and how they can be used as a universal gates. So as you may already know, digital circuits are made up of logic gates that perform specific Boolean operation on their inputs. Some of the most basic type of logic gates includes AND gates, OR gates, and NOT gates. However, NAND and NOR gates have a unique properties which set them apart from the other logic gates. They are considered as a universal gate. This is because NAND and NOR gates have the ability to combine together to simulate the functionalities of all and other types of gates, such as AND gates, OR gates, and NOT gates. So let's try to implement NAND and NOR gates to the three basic gates. So here, as you can see, NAND gate as NOT gate. So dito, pwede nyong, so pag nag-i-interpret tayo ng gate, ng mga logic, depende kung yung process, kung paano mo naintindihan yung logic. So dito, so etong first expression, so first inverter lang yan. So not gate lang yan. So kung ang input, so sa Boolean expression niya is input then output complement. So kung A ang input, A complement ang output. So sa NAND naman, tignan naman natin yung Boolean expression ng NAND. So kung Y equals to, kung ano yung input mo is i-complement niya lang. Since same lang ang input natin dito, same lang ang input natin, so same din ang magiging output. Kung A ang input, A complement ang output. So dito nyo pala makikita kung parehas input ang ginamit natin, yung inverter is same lang siya sa NAND. Then sa NOR naman, tingnan naman natin yung Boolean expression ng NOR. tsaka ng inverter. Inverter, tama. So, dito sa inverter, again, kung A complement, A naman ang output. So, dito naman, ganun din. Kung since same lang ang input. So, kung A complement, A ang output. So, dito nyo pala makikita na yung relationship ng NAND as NOT tsaka NOR as. So, dito naman tayo sa NAND as AND gate. So, dito pwede kang gumamit ng ibang approach. So, dito pwede kang gumamit ng AND, which is ito. Ito AND gate. So, para na maging siyang NAND gate is apply mo lang siya ng inverter. At yung inverter niya. Then, so, ito, may equivalent ka na ng NAND gates to. Basically, NAND gates na yan. So, pwede ka pang maglagay na isa pang inverter para maging AND gates yung output mo. So, pag i-minimize nyo na yung circuit, so meron kayang NAND gates dito, which is ito yung dalawang ito. Then, meron kang isang inverter. Then, balik tayo sa dito sa NAND as NOT. So, yung pag same lang input, yung inverter mo is katumbas din ng NAND. So, pwede natin palitan tong inverter na to dito sa NAND. So, dito pa lang, mapuprove na natin yung NAND gate as AND gate. So, dito naman tayo sa NOR. So, sa NOR gates, tignan natin yung Boolean expression niya. Then, sa AND naman, pwede nyong tignan yung Boolean expression ng AND. A plus B. So, anong pinagkaiba? Yung input niya ay naka-invert. So, sa Boolean expression lang lagi kayo titingin. So, ang gagawin natin dito ay kuha tayo ng NOR gate. Ito yung NOR gates natin. Then, kada input ng NOR gates na yon is invert natin. Ito yung invert natin yan. So, ito, isang input, invert, then balik tayo dun sa natutunan natin kanina. So, pag same ang input, invert, is katumbas niya ng NOR gates. So, pwede mo siyang substitute itong dalawa na tig-NOR gates. Then, ito, isang input lang yan. Same input, same input. So, dito naman tayo sa NAND as OR. So, dito sa NAND as OR, dito naman sa mag-a-apply yung sa ano natin, yung yung NOR as AND. So, balikan natin. So, NAND, hanapin natin yung NAND. Ito. Then, sa OR gates, see? Yung nagbaliktad lang siya, so invert mo lang yung input. So, invert ng input, then balik tayo sa natutunan natin. Pag invert, then same ang input, i-invert niya lang yung output. And pwede na siya yung invert na logic, pwede siya ma-convert sa NAND gates. So, ito yon. Then, dito naman sa OR gates, dito mo naman i-apply yung, kuha mo tayo ng OR. Ito yon, kuha mo tayo OR. Pagkakuha mo ng OR, invert mo siya ngayon para magkaroon ka ng NOR. So, ito, NOR yan. Then, invert mo ulit siya para bumalik siya sa OR gates na output. Then, ito, minimize mo siya dito minimize mo sa OR gates, then balik na naman tayo dun sa natutunan natin, yung pag isang input, then inverter, pwede mo siya ma-convert sa NOR gates. So, balik tayo sa NOR gates. So, since naintindihan na natin, so ito yung mga equivalent ng NAND gates. So, dito naman sa NOR gates, ganun din. So, in conclusion, NAND and NOR gates are considered as universal gates due to their ability to simulate the functionality of all other gates. Kita nyo naman dito. At this part, lahat sila NOR gates. At dito naman, at this part, lahat sila NAND gates. And that's all. Next reporter na po.
Good day, everyone. I am Micko and I am here to discuss about the product of sum representation or the product of sum form. So, product of sum or POS form is used when the output is low or zero. It is the representation of the Boolean function in which the variables are first summed and then the Boolean product is applied in the sum terms. So, there are three types of POS form: the canonical, non-canonical, and the minimal. The canonical form is where the max terms are AND together for which output is false. It is also known as product of max term or canonical conjunctive normal form or the CCNF, and canonical means standard and conjunctive means intersection. Next is the non-canonical. It is the product of some expression that is not in standard form and is called the non-canonical form. It's just the opposite of the canonical. While the minimal form is the most simplified and optimized form of a POS expression which is non-canonical. So, in this table, if the value of the variable is 0, considered as A. If the value of the variable is 1, it is called a complement. So here is an example of a logic gate of minimal form and canonical form. So as you can see, minimal is simplified while canonical is the standard logic gate of the expression. So this truth table is an example for the implementation of product of sum or POS form with an expression of y is equal to the product of a plus b plus c complement multiplied to the sum of a complement plus b plus c multiplied to the sum of a complement plus b plus c complement. So this equation is considered as the canonical POS form. So here is an example of an implementation of product of sum form. So sabi nga kanina, if the value of the variable is 0, it is considered as the product of sum. Doon na i-implement yung product of sum form. So dito sa truth table na to, may tatlo tayong Boolean equation which ang product nila is 0. So yung tatlong yan, ayan, dyan kinuha yung tatlong term dito sa canonical POS form. So first is the a plus b plus c complement. Nagkakaroon lang ng complement if the value of the certain variable is 1. So by solving this, this solution is all about the canonical to minimal POS form conversion. So to get the minimal POS form, we equate a complement plus b is equal to x, and since c times its complement is equal to 0, we cancel the c times c complement here because it is equal to 0, and we equate the a complement plus b into x, and x plus 0 is equal to x, which is the identity law. So we bring down this equation and this equation. We get a plus b plus c complement multiplied to the sum of a complement plus b. Since b is common, we extract b from the two terms. So b plus a plus c times a complement. And through distributive law, we get b plus a times a complement plus a complement times c. So since a times a complement is equal to 0, b plus a complement times c complement is the one left true. So through distributive law again, we get y is equal to the sum of a complement plus b multiplied to the sum of b plus c complement, which is the minimal POS form. So here I made the logic gates diagram for this canonical form or this canonical equation and this truth table, and this one is the minimal logic gates diagram. So next is the implementation of product of sum, in which we convert canonical to non-canonical form. So in this example, we use this truth table. So in this truth table naman, we get 4 Boolean equation in which the product is 0. So we get 4 terms naman since 4 yung products natin na 0 yung value. So by doing what we did earlier, ika-cancel lang tong a times a complement since equal siya sa 0. And since may common sila, which is b plus c, we bring this down. Ayan, kaya napunta siya dito. And this one naman, hindi siya nagalaw, kaya bring down lang din dito. So there is a law in non-canonical form that same but inverted terms eliminates from 2 max terms and form a single term. So to prove it, here is an example. So y is equal to the product of the sum of a plus b plus c plus the sum of a plus a complement plus b plus c. So by doing yung para siyang FOIL method, kumbaga, substitution lang siya bawat term. So ito yung kakalabasan. So kinancel ko lang yung a multiplied by a complement since that is equal to 0, then bring down yung ibang value. So 0 to. Next naman is pinactor out yung mga same variables sa kanila. For example, here, ab plus ac, pinactor out yung a since same variable naman yon. And ang natira is b plus c. Since there is also b plus c here, sabi nga kanina, same but inverted terms eliminates from 2 max terms and form a single term. Kinancel na yan, and ang natira na lang is plus, eto, a plus a complement, cancel din yan since equal din yan sa 0, plus b times 1 plus c na lang yung natira. So 0 multiplied by b plus c is equal to 0, which equates to b plus c. So this one, y is equal to b plus c, is the expression achieved in product of sum form but is still in non-canonical form. So here I also made the logic gates diagram for the canonical, which is this truth table, and the non-canonical logic gate diagram for this expression. That's all. Thank you.
We will now move to the SOP, or the sum of product circuit implementation using K-maps. So what is the sum of product SOP? So here's an overview. According to electronics tutorial, sum of product form is a Boolean algebra expression in which different product terms from inputs are summed together. So basically, ang SOP ay yung pag-add ng mga products of each inputs. So kunwari, dito sa example, AB plus ABC plus BC. So pinag-a-add lang yung mga products ng AB, ng ABC at ng BC. Ito naman sa next example, pinag-add ang products ng A naught, B naught, C naught plus C plus AD. So, dito sa ilalim, makikita na isang buo yung bar o yung nut sa ABC. So, hindi yun pwede. Dapat each term lang ang may nut. Tapos, dito sa right side, ito naman yung logic gates for SOP. So, di na tayo mag-dig in dyan. Mag-move na tayo sa K-mapping. Let's say, for example, we have this given. The function y is equal to the sum of min term 1, 5, 7, 9, 11, 13, and 15. So, basic given, ang gagamitin natin ay ang 4 variable table. So, kailangan muna natin mag-drawing ng table with 4 columns and 4 rows. Sa columns, kailangan natin ilagay itong mga numbers. 0, 0, 1, 1, 1, 1, 0. Ganon din dito sa rows. So, mahalaga yung pagkakasunod-sunod neto kasi masisira yung buong K-map nyo. Lalagyan natin ng min term. So, dito sa 0, 0, tandaan nyo pa yung shortcut na 0, 0, 0, 0. Yung 2 raised to n. So, dito, 2 raised to 0, 2 raised to 1, 2 raised to 2, tas 2 raised to 3. Dito, since 0, 0, lahat, ibig sabihin, turn off lahat yan. So, 0 ang min term. Dito naman, ang naka-on lang ay yung 0, 0, 0, 1. So, 2 raised to 0. So, 1. Dito, 0, 0, 1, 1. So, 0, 0, 1, 1. So, 2 plus 1. Kaya 3 dito. Dito naman, 0, 0, 1, 0. So, ito lang yung naka-on. So, 2. Dito naman, 0, 1, 0, 0. Ito lang yung naka-on. Tapos sa last, 1, 0, 1, 0. Kaya 8 plus 2, 10. Ngayon naman, titignan natin yung base sa given. Dito na tayo magmamapping. Lahat ng values sa given, lalagay natin ng 1 dito sa table. So, 1. Sa min term na 1, lalagay natin ng 1. Sa 5. Sa 7. Sa 9. Sa 11. Sa 13. At sa 15. Yung the rest, lalagyan lang natin ng 0 para di tayo malito. Ngayon, mag-group na tayo. So, ang pag-group ay nakabase sa priority. 2 raised to n pa rin. So, 8, 4, 2, at 1. Ay kapag mag-group pala, pwedeng vertical o horizontal lang. Bawal lang diagonal. So, ganito lang pwede. So, mag-group muna tayo. Ito, 4 to. Tapos, ito, 4 din to. Tapos, ito, pag nakita nyo, isa lang siya, diba? Bawal yan kasi, nasa list priority siya. Kung to naman, ganun din, nasa list priority siya. Pwede pa tayo makabuo ng 4. Lalagyan na natin siya ng label. So, ito muna tayo. So, dito sa rows, makikita natin yung may common term ay yung B. Kasi 0, 1, tas 1, 1. So, alin ba dito yung may common term? Ito, A to, tong 0, 1. Itong B, 1, 1. Kaya B yung sa row natin. Ito naman sa column, kapag tinignan natin to, ang common term niya ay yung D kasi sa C, 0 at 1. Pero yung D, 1 at 1. Kaya BD. Ito naman sa isa pang group. Ito yung titignan. Yan. Ang common term ay yung A kasi 1, 1. Yan. A. Yung B, 1, 0. Kaya ang ilalagay natin ay A sa row. Dito naman sa column niya, ang common term ay D kasi sa C, 0 at 1. Pero hindi niya 1, 1. Kaya AD. Tapos, ang last naman, ito, itong nag-iisa. Bali, ang mangyayari, kasi wala siyang ibang ka-row. Tingin lang tayo dito sa column. So, ang C natin, magkakaroon ng bar kasi 0 siya. Tapos, since may 1 pa dito, ito na yung D. So, ang final answer natin sa SOP expression, CD plus AD plus BD.
A multiplier is a circuit using a root to end the several input signals to a single output. A simple example of a non-electric circuit of a multiplexer is a single-pole multi-position switch. Multi-position switches are widely used in many electronic circuits. However, circuits that operate at a high speed require the multiplexer to be automatically selected. A mechanical switch cannot perform this task efficiently. Therefore, multiplexer is used to perform high-speed switching that are constructed of electronic components. So, this multiplexer is a circuit used to select and route any one of the several input signals to a single put. It is also a multi-position switches that are widely used in many electronic circuits, and the multiplexer is used for digital application, which also called digital multiplexer. It is a circuit with many input but only one output. By applying control signals, also known as a select signals, we can steer to any input to the output. Some of the common types of multiplexer are 2 to 1, 4 to 1, 8 to 1, 16 to 1 multiplexer. So next. So this figure shows the general idea of a multiplexer with n input signal, m control signals, and 1 output signal. The 4 to 1 multiplexer has a 4 input bits, 2 control or select bits, and 1 output bit. The 4 input bits are D0, D1, D2, and D3. Only one of these transmitted to the output Y. The output depends on the values of A and B, which are the control inputs. The control input determines which of the input data bit is transmitted to the output. When AB equals to 0, 0, and the upper AND gate is enabled, while all the AND gates are disabled. Therefore, data bit D0 is transmitted to the output, giving Y equals DO. Next po is the multiplexer. So, the multiplexer is a digital combinational circuit which takes one input signals and generates multiple output signals. It is known as the multiplexer or DMUX, as it attributes a single input signal over many output lines. Hence, it is also referred to as a type of data distributor. In the multiplexer, there is only one input line and two output lines, where n denotes the number of the select lines. Therefore, it can be noted that the multiplexer serves as the operation of multiplexer. Next. The multiplexer means the one-to-many. A demultiplexer circuit with one input and many outputs. By applying control signal, we can steer any input to the output. Few types of demultiplexer are 1 to 2, 1 to 4, 1 to 8, and 1 to 16 demultiplex. Next. So in this figure, it shows that the general idea of the multiplexer with one input signal, M control signals, and N output signals. Then the input bit is labeled as data D. This data bit is transmitted to the selected output lines, which depends on the values of A and B. The control or select inputs. When A, B is equals to 0, 1, the second AND gate from the top is enabled while the other AND gates are disabled. Therefore, data bit D is transmitted to the output Y1, giving Y1 equals data. If D is low, Y1 is low. If D is high, the Y1 is high. The value of Y1 depends upon the value of D. All other outputs are in low state. If the control input is changed to A, B equals 1, 0, all the gates are disabled except the third AND gate from the top. The D is transmitted only to the Y2 output and Y2 data.
Hello guys, I'm John from Vincent and I will do code conversion to binary. First, BCD to binary. Binary coded decimal or BCD is a set of binary encodings for decimal numbers used in an early digital computers. In BCD, a binary sequence is used to represent each digit of the source decimal number. And binary is the numeric system of computers, which is binary numbers have a base of 2, and computers only understand 0 and 1. And for example, 001100 BCD to binary. Step 1 is we convert BCD to decimals. So we group this into 4 bits. That's why we separate this into 2. And the first group is 001 and the second group is 1100. Then we will multiply it by right, from right to left by 1, 2, 4, 8. Then we'll get the sum. And first we'll multiply the first group. 0 times 1 equals 0. 2 times 0 equals 0. 4 times 0 equals 0. Then 1 times 8 equals 8. So the sum of this is 8. In the second group, 1 times 1 equals 1. 1 times 2 equals 2, 4 times 0 equals 0, 8 times 0 equals 0, so 2 plus 1 equals 3, so the decimal number is 38 base 10. Next slide. We continue this from decimal to binary. So how we can get that? We divide the 38 from 2, so we get the successive quotient with a base of 2. 38 divided by 2, the quotient is 19, remainder 0. Then 19 divided by 2, the quotient is 9, remainder 1. 9 divided by 2, the quotient is 4, remainder 1. 4 divided by 2, the quotient is 2, remainder 0. And then we will get 2 divided by 1. We will stop at this 1 because 1 is less than 0. So we will write this from bottom to top, so which is 100,110 base 2. We'll get the answer. From BCD to binary, we get a 001100 BCD is converted into binary, which is 100,110 base 2. Next slide. The next slide is code conversion XS3 to binary. I will be teaching you how we can convert XS3 into binary. We get an example of 010111 XS3 into binary. In the first step, we'll make the group of 4 bits and write the equivalent decimal number from the XS3 table. We will be familiarizing with how we can get an XS3 table. So first we group this into 2, separate this into 4 bits, and then we'll multiply it into 1, 2, 4, 8. The first group is 1100. We'll multiply this
by 1248. 1 times 0 equals 0. 2 times 0 equals 0. 4 times 1 equals 4. 8 times 1 equals 8. So 8 plus 4 is equals to 12. Then we'll subtract this by 3, which is 9, because that's how we can get a decimal number equivalent to excess 3. The second group is 0, 1, 0, 1. From right to left, 1 times 1 is equals to 1. 2 times 0 equals 0. 4 times 1 equals 4. 8 times 0 equals 4. So 4 plus 1 is equals to 5 minus 3, which is 2. 29 base 10 is the equivalent decimal number in the excess 3 table. Next slide, please. At last, we find the binary number of the decimal number using a decimal to binary conversion, as we used earlier from BCD to binary. So we divide 29 and we get the successive quotient from the base 2. 29 divided by 2, the quotient is 14, remainder 1. 14 divided by 2, the quotient is 7, remainder 0. 7 divided by 2, the quotient is 3, remainder 1. Then 3 divided by 2, the quotient is 1, remainder 1. And then we will stop at 1 because it is less than 2. Then we will write this from bottom to top. We can get 1101 base 2. We now convert the decimal 29 base 10 into the binary 1101 base 2. We have now an answer, which is 0101100 excess 3 to binary 1101 base 2. That's all. Thank you.
Hello everyone, my name is Micko GARCIA and I'm here to present on how to convert BCD to gray code and vice versa. So first, let us know what gray code is. Gray code, also known as cyclic code, reflected binary code, or gray code, is defined as an ordering of the binary number system such that each incremental value can only differ by 1 bit. In gray code, while traversing from one step to another step, only 1 bit in the code group changes. That is to say that two adjacent code numbers differ from each other by only 1 bit. So now, I will demonstrate how to convert BCD to gray code and will demonstrate later the vice versa of gray code to BCD. So, first, let us have an example of 0101 to convert it to gray code. So the binary number of 0101 is 5. So in converting gray code or BCD, we have to remember the truth table of XOR, which we'll be using in the conversion. So the truth table for XOR is if AB00, the output is 0, 01 is 1, 10 is 1, 11 is 0. So remember, if the input are the same, then it's equal to 0. And if it's different, then it's 1. So now that we have the truth table, we can now use it to convert 0101. So 0101, first, we get the MSB or the most significant bit, which is 0. The first number, 0. Then we compare the first two numbers, 0 and 1, which is equals to 1. Then next is 1 and 0, which is also equals to 1. And lastly is 0 and 1, which is different. So the answer is still 1. So the gray code is 0111. So next, let's convert gray code into BCD. So let's just use the answer from the example. So let's use 0111. So as you can see, the method for converting gray code to BCD is different from BSD to gray code. So in converting gray code is first, we get the MSB or the most significant bit and drop it down, and after that we compare it to the next number, which is 1, and we will still use the XOR truth table for the conversion so 0, compare it with 1 is 1, and 1 and 0 is 1, and drop it. So there, the converted answer is 1. So the answer is 0101, which is the same to the example given before. Thank you for listening, and the next reporter is Mr. Francis CAYCO, which will be discussing latches. Thank you.
Hi, so good day everyone. I am Francis Marcaico and today I am going to discuss to all of you about latches. What do you mean by latches? So latches are considered as the basic storage of circuits in binary form. So latches have the ability to replicate the previous output of the circuit when a certain signal is applied. So we'll see about that as we go on to the discussion. So the ability of latches to replicate the previous state is due to the existence of feedback. So if we are going to look at the circuit, you can see that the AND gate's output is an input to the reset or below of the NAND gate. So that is the feedback path of the latches. Latches operates on signal levels rather than signal transitions. So what do you mean by signal levels? So signal levels are the output that is dependent on both the circuit's previous and the current input. So whenever the input changes, the output changes. So latches are different from signal transitions. These are the circuit that rely on a clock that turns on or off periodically. So in signal transitions, signal levels only matter when a clock is turned on. So when we say asynchronous, data or signal is triggered immediately. So in latches, there are two inputs, which is set and reset. So the output of set is Q, whereas the output of reset is not Q. So Q and Q complement must invert each other or complement each other. In this presentation, we are going to use NAND latches. So now we're going to proceed with the first case, wherein the initial conditions are S is equals to 1 and R is equals to 1. So we're going to illustrate how these NAND latches work. Since our initial conditions are S equals to 1 and R is equals to 1. According to this presentation, the previous stage is Q is equals to 0 and Q naught is equals to 1. So the Q naught will serve as the input for the S or set. Meanwhile, the value of Q serves as an input for R. So based from the NAND truth table, we can see that then the next state when 1 1 1 AB, so 1 1 is 0, and then next, and the 0 and 1, which is this one, the output will be 1. So when we try to again to repeat the iteration, we say in the second iteration, our inputs are still 1 1 1, since the previous states are still 1 and 0, outputs are still the same. We can see that when both inputs are 1, it simply reflects the previous state of this circuit. The output is the memory. Proves that latches are considered as a storage element. So now we're going to proceed with the second case, wherein the initial conditions are S is equals to 0 and R is equals to 1. So like before, we are going to illustrate. So since the value of S is 0 and the value of R is 1, according to this truth table, so when one of the values or the inputs are 0, this one, then the output will be automatically 1. So from this S, then the Q will be 1. Output of Q will be the input of R, so 1 and 1, then the output will be 0. So now in second iteration, when our inputs are still 0 and 1. So since the value of previous Q is 1, or let's simplify it further na lang. So since the value of S is still 0, then the output will be 1. And the same goes with the value of the output of R for reset. Therefore, we can say that when the S is equals to 0 and R is equals to 1, then the Q will be 1 and the Q naught will be 0.
And now, for the third case, so this is almost similar as second, so let's just go through this quickly. So when S is equals to 1 and R is equals to 0, based from the truth table, so when 1 is 0, then the output will be 1, as shown in the Q naught. So the output of Q naught will serve as an input for the set, so 1 and 1 will be 0. So when S equals to 1 and R is equals to 0, then the output of Q will be 0 and the output of Q1 will be 1. And even if we try to replicate or increase our iteration, so the output will be the same. And now we're going to proceed with the fourth case. So when the initial conditions are S is equals to 0 and R is equals to 0. According to the NAND truth table, so when one of them has a 0 on it, then the output will be automatically 1. So for the S, the output of U will be 1. And for the R, so since the value is 0, then the output will be 1. So we notice that when Q and not U are equal, is 1 and 1. As you can see, it already violates the provisions that I've mentioned earlier. That is, we should not obtain a value of 1 and 1 or 0 and 0. So the values must either be 0 or 1 or 1 and 0. Even if we try to go on with the next iteration, let's say for the second iteration, we try to input again 0. So since the value of 1 will be serve as an input for both, then the output will be both 1. Even if we try to make another input, let's say 1 and 0, we are going to try to input 1 and 0. So since the previous states are 1 and 1, so the value of 1 will go through as an input for the reset and also for this one. So since both of them are for the S, the output will be 0 and the output for R will be 1. So if we try again to make our input as 0 and 0, value of S and R will be 0. So 0 and 1 will be 1 and the C1 and 0 will be 1 again. So in conclusion, when S equals to 0 and R is equals to 0, you should avoid using this type of combination as it violates the pre-existing conventions that Q and not Q must complement each other. So now we are going to attempt to integrate the previous three current inputs with the exception of the fourth ones. So now let's say that our first inputs S and R 1 and 0. So 1 and 0. So the output of R will be automatically 1 and will be part of the input for set, and the output of Q will be 0. So let's record that one. So for example, for our second iteration, we have included S and R which is equal to 1 and 1 respectively. R is equals to 1 and Q is equals to 0. So for the second iteration, so 1 and 1 which is equals to 0 and 0 and 1, 1. So therefore, this is the same as memory. Since we have already discussed the four possible inputs of a NAND latch, so now we are going to summarize it. Based from the truth table you've seen on the right side, when S is equals to 0 and R is equals to 0, so the output is not be used. So when S is equals to 0 and R is equals to 1, so the output Q will be 1. So when is equals to 1 and R is equals to 0, so the output will be 0. So whenever S and R are both 1, it should retain the previous memory of the circuit. So now we're going to briefly discuss NOR latches. This is similar to NAND latches, but in this case, instead of using NAND gate, we are going to use NOR gates in both in set and reset. So the output are almost similar, but in some ways they are inverted. I mean, when NAND gates inputs are 0 and 1, the outputs will be 1 and 0 respectively. However, in NOR latches, when R and S are 0 and 1, the output will be 0 and 1. So therefore, you'll notice that there are no inversions of outputs. Same goes when R and S is 1 and 0, the output will remain 1 and 0. So there's another major difference. For NOR latches, when both R and S are zeros, the output will be memory. However, when both of them are 1s, then it shouldn't be used. So this is another opposite compared to NAND latches. So that almost ends my reports for latches. Although there are still different types of latches such as JK latches, T latches, and D latches, so this will be reported by the following presenters. Although the only difference that those are flip-flops and I'm talking about latches. So the only difference that latches are level triggered whereas flip-flops are edge triggers. So that ends my presentation. Thank you so much.
SR flip-flops. Basically, SR flip-flops, just like latches, no? The main difference lang is in a flip-flop, there is a gate or an enabler. Flip-flops are edge triggered, unlike latches are level triggered. The difference being
level triggering have outputs that can change as soon as the inputs change, and flip-flops have outputs that will only change when a control signal, like the enabler or the gate or the clock, goes from high to low or low to high. Here we can see two flip-flops, NAND gated, NAND SL flip-flop, and a gated NOR flip-flop. As we can see, meron tayong presence ng enabler, yung E. So nakikita natin yung E dyan. Ayan po yung enabler natin. Quick tip lang, as long as the enabler does not go to high, no change in the data will be done. And this also applies to the AND-gated NOR line. Let's go to the derivation of the truth table. Pag yung enabler natin ay 0, wala na kagad mangyayari sa outputs natin. You can put X here to signify no change. Kung meron naman tayong 0, 0 sa S and sa R, no? And we have 1, example. If we have 0 and 1, meron tayong truth table ng NAND dito, 0 and 1, we will have 1. 1 and 0, we will have 1. For example, yung previous state niya is 0 and 1 din. So, kung 0 dito, magkocross lang yan. 0 mapupunta dito. 0 and 1, we will have 1. 1 magkocross din dito. 1 and 1, we will have 0. So, yung Q natin in our first derivation is 0. And ang Q bar natin is 1. So, tama kasi magkabaliktad sila. Ayan. Now, let's have a 0. 0 yung set and 1 yung reset. Ano mangyayari? Well, of course, 1 din to. 1 and 1, we have 0. 0 and 1, we have 1. Ang outputs nila nung nakaraan ay 0 and 1. So, yung 0 dito, 1 dito. 1 and 1, we will have 0. 0 and 0, we will have 1. So, yung Q natin hindi nagbago kasi wala naman siyang laman eh. So, kahit i-press mo yung reset button, no, walang mangyayari doon sa ating output Q. Ngayon, let's have set as 1 and reset 0. Of course, 1 to. 1 and 1, we'll have 0. 1 and 0, we'll have 1. Ano yung nakaraan niya? Yung nakaraan yung Q ay 0 and yung Q bar is 1. Right? 0 and 1, magkakaroon tayo ng 1. That will cross over here. 1 and 1, magkakaroon tayo ng 0. So now we can see only when we trigger the set and the enabler, magkakaroon tayo ng pagbabago sa output Q natin, which we have derived na magiging 1 and magiging 0. Katulad lang ng ating latches, no? Pero ang kailangan natin ay enabler. Okay, next. Ano nga ba ang D flip-flop? Ang D flip-flop, in layman's term, D flip-flops are used to hold data. And this is derived from SR flip-flops. A change is made so that one data input can trigger both inputs for S and R using an inverter. And if D is equals to 1, then S equals to 1, and R equals to 0. Ano nga pinagsasabi ko? So here, meron tayong simplified na truth table ng SR flip-flop. Makikita natin, if we look carefully, magkakaroon lang yan ng change. Itong memory and itong invalid, no change yan. Itong magkakaroon lang tayo ng change if magkabaliktad yung S and R natin. For example, S is 0, 1 is 0. R is 1. S is 1, R is 0. So, may nakaisip na maglagay tayo ng inverter so that we can pass data, no, to the input of the IC. Ayan, sinimplify nila to. Itong naka-line na to. Basically, nasa loob ngayon ng circuit. How does the D flip-flop store data? Katulad lang sa SR flip-flop, kapag hindi mo prenes yung S or hindi mo siya in-excite, hindi magkakaroon ng output Q or hindi mag-i-store ang data. So let's have it. No? Using the truth table here from the SR flip-flop, halimbawa ang clock, syempre, pag 0 muna, yung clock natin, katulad din sa SR, hindi rin magbabago. Kapag ang D natin ngayon, ginawa natin 1, imagine the data flow. Yung 1, papunta dito, papasok sa S. Ang S natin, automatically 1, di ba? Papunta dito, yung 1, may invert, magiging 0. R natin 0. So, ano mangyayari? S1, R0, output will be 1. And this will never change unless magpapass tayo ng 0 sa set natin. How does that happen? Same lang. Same lang sa kanina. Example, we pass 0 going here. Magiging 0 na kagad automatically yung set. And if magpass yung 0 dito, may invert, magiging 1 yung reset. So, it resets the IC. Yung Q natin will go back to 0. And that's basically a D flip-flop. Next reporter.
Hey everyone, I am Justine Marquez. So this section concludes our report devoted entirely to discussing JK and T flip-flops. So the JK and T flip-flops are two examples of digital logic gates that have seen less frequent use in system design. So first we will go to the JK flip-flop. So a JK flip-flop is simply an SR flip-flop with feedback added. So this feedback selectively enables one of the two set reset inputs not to transmit an activation signal to the multi-vibrator circuit. So it also removes the invalid condition. So in figure 5.12, it depicts the circuit diagram of a JK flip-flop constructed with a D flip-flop and K state. So we are here in the table for JK flip-flop with a constructed with a D flip-flop. So when the input for J is equal to 1 and K is equal to 0, then D is equal to 1. Then the next clock edge sets the output to 1. Then when the input for J is equals to 0 and K is equal to 1, so the next then D is equals to 0. So the next clock edge resets the output to 0. Furthermore, when both input for J and K is equal to 1, then D is equal to not Q. The next clock edge complements the output. Finally, if both input for J and K is equal to 0, then D is equal to Q. The clock edge leaves the output unchanged. Next slide. So now we are going to the characteristic table of the JK flip-flop. So the characteristic table for the JK flip-flop shows that the next state is equal to the present state when inputs J and K are both to equal 0. So if both inputs for J and K is equals to 0, the clock edge leaves the output unchanged or no change. Then when input for J is equal to 0 and K is equal to 1, and then Q close open parenthesis T plus 1 is equals to 0. So the next clock edge resets the output to 0. Furthermore, when the input for J is equal to 1 and for K is equals to 0, then Q close open parenthesis plus T plus 1 is equal to 1. So the next clock edge sets the output to 1. Finally, if both inputs for J and K is equal to 1, then the condition for this will be implemented as Q close open parenthesis T plus 1 close equals to not Q. So the clock edge complements the state of flip-flop. So that is all for the JK flip-flop. So next topic is the T flip-flop. So T flip-flop refers to toggle flip-flop. So it modifies the output at every clock edge and generates an output with half of the signal frequency at the input. So you can see in the picture, the toggle flip-flop is a complementary flip-flop that can be derived from a JK flip-flop by connecting inputs J and K. This is depicted in figure 5.13. So the T flip-flop, it can be derived as JK flip-flop by connecting inputs J and K. So if T is equals to 0, a clock edge does not affect the output, whereas if T is 1, a clock edge complements the output. If T is equals to 0, does not affect or no change or unchanged. And if T is equals to 1, then it complements the output. So for designing binary counters, the complementary flip-flop is useful. So now we will go to the characteristic table of T flip-flop. So only two conditions will be input in the table for T flip-flop. So these are the two conditions. When the input of T equals 0, the clock edge does not change its state. And if the input of T is equal to 1, then the clock edge complements the state of the flip-flop. So as we can see in the table, if D is equals to 0, then it doesn't change its state. And if D is equals to 1, then it complements the state of the flip-flop. That's all. Thank you for listening.